Hey, AB Calculus, this is chapter 41, part 2. I'm going to do a couple more examples. Did I say this is Mr. Canfield? Because it's not. Today, it's still Mr. Canfield. Okay, I gotcha. Oh, man, I tricked you. Okay. Bacteria in a lab grows in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. That's our key that I can use. dP dt is equal to kt, that then leads to P is equal to CE to the kt. Guaranteed that's the solution to this. So suppose there are 3 million bacteria initially, and 3 hours later, that number has doubled. Oh, okay. So I know that if there's initially 3 million, I could go into here and I could go when t is 0, population is 3 million. That means this C right here is 3 million. I'm going to use just the number 3, and I'm going to represent my numbers in millions here. So P is equal to 3e to the kt. And it says 3 hours later, that number has doubled. So I'm able to solve for this k here by saying, well, I know I've got 6 million at 3 hours. And so now I can go in and I can solve for k. So I'm going to solve completely symbolically. I'm not going to use any calculator for this. So divide both sides by 3, we get 2. 2 is equal to e to the 3k. We'll ln both sides. We get ln of 2 is equal to 3k. So k is equal to the natural log of 2 all divided by 3. So our differential equation then is going to be dp dt is equal to ln2 over 3p. kp, right? Oh, I wrote this wrong. kp. It's early enough in, I'm going to leave that. So we have our differential equation, and we also have our population equation, right? This is not a differential equation because there's no derivatives in it, but this is an important equation as well. So what would the bacteria population be 1 full day after the first measurement? So that's where you could just go in and so t was in hours, so that'd be 24. I'd plug in 24 for t, get some number here. How long will it take for the population to grow from 1 billion to 2 billion? So we would need to find out, well, 1 billion is 1,000 million, so that's 1,000 to 2,000. So we could 3e to the ln of 2 divided by 3x, all right? So I could go into my table here, and I'm gonna, oops, that's not what I meant to do. I'm gonna go into table set, change it to ask, just to find out, like, when do I even hit 1,000? Is it 5 seconds in? No, or 5 hours in? What about 100 hours in? Oh, yeah, that's a lot. Okay, 10 hours in, 20 hours in, 30 hours in. Okay, so 30 hours, I'm at 3072. At 25 hours, I'm at 967. All right. Oh, I'm doing this the dumb way. Wait, no. That wasn't like the dumbest thing I could have done. So now I know around like 25 to 30 hours is when the stuff happens. So what I'm going to do is I'm going to go to my window, and I only care about 25 to 30 hours. So I'm going to go from 25 to 30. And my y scale, I'm going to go from let's go from 500 to 2,500. So that's covering these y values. These are my populations, and I can find out the time when I hit 1,000 if I go into y equals, and I do a 1,000, and then I do a 2,000. Cool. So I can just find the times when it hits those. So I'll do my intersect function, and I got to go down. Oh wait, no I don't. I just got to click enter here, and then I can select which one I want to hit. So I want to hit the bottom one first. So it looks like 25 point, this happens at 25.142 hours, and 2,000 happens at, okay, still on the curve, this guy, 28.142. Wait a minute, what? I didn't need my calculator for this. Look at that. Those are 3 hours apart. Oh, I feel dumb. You know, it says 3 hours later that number has doubled. 1 billion to 2 billion is a number doubled. The idea of exponential growth is over a certain amount of time, it's gonna like, it'll double in the same amount of time every time. Why isn't the world inundated with bacteria? No, I don't know. I feel like it's a silly question. Why isn't the world overrun with anything? It's not a silly question. If we look at the mathematical model, clearly we're supposed to have basically infinitely large numbers of bacteria, of people, of different things. It's because stuff dies, stuff kills other stuff, stuff eats other things. There's limiting factors like buildings, and there's only so much bacteria that can grow on my desk because my desk is only so big. Lots of reasons. We actually get into this a little bit more in BC. It's a really cool, really cool thing that happens. All right. A manufacturing company determines that once it's started a new TV advertising campaign, its monthly change of sales is proportional to the current monthly sales. Ooh, look at that. So we know dP/dt is equal to KT, and we know that P is equal to CE to the KT. Okay, has to happen. So that's what that was our little key phrase. In January, it sold 5,000 units, and in April, it sold 7,000 units. Okay, so if we're gonna say that we start in January, then we could say that this C is 5,000, our initial amount. We'll just say our initial sales is 5,000, right? So and then in April, it sold 7,000. Let's see. So if January is 0, then February, March, April would be 3. So when T is 3, P is 7,000. And so we can go through and solve like we've done before. So we'll divide both sides by 5,000, and it'll be 7 over 5 when the thousands cancel. And we'll ln that. So we'll get ln of 7/5 is equal to 3k. And then we'll divide that by 3. So that's our k value is going to be ln of 7/5 over 3. And then we can say, I feel like ln of 7/5 over 3, that something seems wrong here. ln of 7 over 5. No, okay. Oh, I know it doesn't. All right, ignore me. Okay, pay attention to me again. So the differential equation is going to be, it says write and solve. I don't need to write and solve if I know this. But our differential equation is going to be dp dt is equal to ln 7 over 5 over 3 k. Can't seem to write the correct. I did it again. Kp. I'm so used to x being on the right-hand side. Don't make my mistake. So then our population equation is going to be 5,000 e to the ln of 7/5 all over 3t. All right, so that's the differential equation, and that's it solved. How long will it take for sales to go from 10,000 to 15,000? Oh. So, this time, I think, yeah, this time I can't just go. So 5,000 to 7,000, that's times like 1.4, I think. And 10,000 to 15,000 is not times 1.4. So I know that it'll take, this is times 1.5, right? So I know it's going to take a little bit longer than 3 months because that's what it was last time. And I could do it the same method as I did here. And we'll just move into the last one. Radioactive decay is measured in terms of half-life. Sorry, that's a dead meme. All right. The number of years for half of the atoms in radioactive material to decay. The rate at which radioactive material decays is proportional to the amount present. It's one of these. Are you surprised? If 8 grams of the plutonium isotope plutonium-239 was released in the Chernobyl nuclear accident, how long will it take to decay if 1 gram is a half-life of 24,360 years? Okay, so we can figure this out, and there's some extra numbers in here that throw us off. Pu 239, so plutonium-239, these are just like different, it's a different isotope. Oh, what's an isotope? It's like the configuration of electrons is like slightly different or something like that, but it's radioactive. And side note, I haven't done a ton of research into Chernobyl, but I've looked into a lot of other, they call them like criticality accidents. And it's gross, but it's really interesting the way that the radioactive material behaves and what it does to the human body. Like it's super fascinating. It makes all that stuff that happened during World War II really tragic when you think about it. I'm not saying they shouldn't have done what they did or they should have done what they did. I'm just saying the devastation that comes from nuclear misuse or nuclear violence is incredible. And radioactivity is not to be toyed with. So anyway, all right, okay, so I know that 8 grams was released. Okay, so we'd be like, our initial population was 8 grams. And I know the half-life is 24,360 years. So I'll make time in years. And I know that if I start with 8, then I end with 4, because that's what half-life means. Right? And we just got to find out what k is. So we'll divide both sides by 8. We get a half. So then we'll ln it. So we get ln a half is equal to 24360k. And divide both sides by that. And whatever this is k. And what I'm going to do is I'm actually going to store that, because that's a nasty number. ln a half divided by, wait, it's a negative number. That should make sense if we think about, oh, this is a shrinking thing. So I'm going to store this as alpha k. So now for this problem, I can actually just use k in my calculator and not have to type this thing every time. So I know then dp dt is equal to k, or ln a half, over 24360 p. I wrote the right thing this time. So how long will it take to decay to 1 gram? So what I'm going to use is, I know population is equal to 8e to the kt. So I want this to decay to 1 gram, which is 1 over 8. Oh, that's silly. It's 3 half-lives, right? It's just decaying to 1/8 of its original. That's just 3 half-lives. So it's just going to be triple that. Let's say you didn't see that. So now we'll ln it. So ln of 1/8 is equal to kt, and we'll just divide both sides by k. And we know that k is this guy. So we can just do ln of 1/8 divided by alpha k. And wow, I'm so surprised that the answer looks like it's exactly 3 times 24,360. Wow. So, cool. There. I love radioactive decay problems. They're super interesting. You've probably seen them in chemistry class, maybe even physics. But yeah, that's is there a chapter 42? I feel like there's a chapter 42. If you've watched this far and there is a chapter 42 and you want me to do chapter 42, I'll do chapter 42. But part of me thinks that I am spending more time on these videos than any of my students are. And hey, if that is not true, I would love for you to get in my face about it and be like, that's not true, Mr. Canfield. I watch your videos, or I do all the work I'm supposed to do. Like, I'd love to hear that. And I mean, those of you that watch it at 1.5 speed, then yeah, of course you're spending less time than I did. But like, that's not what I mean. I mean, I see the view count. It's depressing that more students don't do what they're supposed to do. But it's been a weird year. I guess this means that in the future I need to refilm this video, because hopefully it won't be a weird year every year. But yeah, hope that was helpful. As usual, you know where to find me. Bye.